It's September 21st, 2020. We'll call this video Density Flying. Those of you guys who have studied physics or science in general, you may know that all matter has density. Density is a measure of mass to volume. And we'll stop right there because I've already lost some of you. Anyway, the person who specializes in thought experiments shapes the future. You are just as capable of being Einstein as Einstein was. So a simple way to explain density is imagining one of those little oil, water, syrup projects where you get a little lava lamp type of jar. You stick the syrup in there, and then you stick the water with coloring in there, and you stick the oil in there, and you stick various liquids, and you see how they make these little dense layers. Because the syrup is more dense than water, and therefore the water with food coloring or whatever will sit on top of the syrup, and the oil is less dense than the water, and so the oil will sit on top of the water, and they'll separate by a line, a visual line that you can see. People tend to forget that this air that we live in is dense too. There's molecules of oxygen surrounding us. It's not nothing. And sometimes when you measure in science, you forget there's not nothing there in front of you. It's something. It's oxygen. But, and even if you go up into outer space, it's still not nothing. There are still hydrogen atoms and helium atoms. And it's far less dense, but it's still, there's something there. But, you know, when we come back to oxygen, where we are now, they say that it's 99% vacuum. In other words, it's not very dense. You can zip through it in an airplane because the oxygen is 99%, you could say nothingness, as far as we know scientifically. But there is oxygen molecules. I can feel them as I wave my hand through the wind. Those are oxygen molecules. And since we're on the topic, the atmosphere of the Earth and the water on the Earth and the dirt on the Earth and the metals on the Earth create those layers like you see in that little lava lamp experiment. And that is the breakthrough. That's the thought experiment that may take us to the future here. When you think about how a boat floats in water, ask yourself how a 200,000 ton cruise ship can sit in the water and not sink. It's pretty impressive, but it has to do with density and the organization of those layers in dense atmosphere. Now, we all know a cruise ship, and most boats, of course, displace the water so that oxygen fills most of the compartments of the boat, because oxygen is far less dense than water. And technically, water is 784 times more dense than oxygen. So water will always fall. We are blessed to be able to see very clearly the very fine line of separation between oxygen and water. But the separation between them is very, very fine. I mean, you could be at this position, and then you could drop a millimeter, maybe a micrometer, and be in water. That's how thin the separation between oxygen and water is. And the cruise ships and any boats use that to their advantage because we clearly see the separation point. And it's easy to fill a compartment of steel with a hole with oxygen and surrounded by water, which is much greater in density, and have it float. Okay, now, but let's step to the future here. Let's take a trip to the future with me, and to the past as well. The oxygen in our atmosphere, and our atmosphere has many layers. We live in the troposphere, and above that is the stratosphere, where there's less oxygen because there's less oxygen molecules. And above that, finally you have the ionosphere, where that is the border to outer space, technically. And there's very much less oxygen in each sphere you go to. The layer between oxygen and outer space is much greater than the layer between water and oxygen. We're talking 37 miles to 190 miles of space, of transition between oxygen layer and outer space layer, where there are helium and hydrogen atoms. Let me explain how a submarine works. Because if you understand how a submarine works, then you might be better prepared to at least give it a shot in your brain to see how the future could work in flight. A submarine has ballasts, and those ballasts, you know, the submarine is shaped like a pill, and on the surrounding sides of the pill you have ballasts, which are compartments which fill either with air or with water. And if you fill them with water, then there's more weight to the whole submarine, more density, and the submarine drops at will. Now, because the submarine is more dense, it drops, and you can actually replace that water in the compartments with air once again. And once you do that, the submarine floats up. And this is how submarines function, through ballasts. My proposal is simple. If we have these layers of density, and if you watch these links that I'm going to share with you, you can see how these layers of different liquids, you can actually drop a bottle cap, and the bottle cap will sink to the bottom of the oil, but not sink down into the water, the colored water, because the bottle cap is slightly more dense than the oil, but not more dense than the water. The point is, these density layers are a scientific law unto themselves. Okay, that's what science is in a nutshell. We don't make up the rules. We observe what nature shows us through science, and then we follow those rules. That's science in a nutshell. So, by science's rules, could we not fill a container with outer space and use it to float in the oxygen atmosphere? It will be less dense because hydrogen molecules in outer space occupy about 1 atom per cubic centimeter. Now, to give you an idea what that means, when I tell you that there is 1 hydrogen atom in outer space, between all the stars and between the planets, in interstellar medium, ISM, in space, you have 1 hydrogen atom per cubic centimeter, on average. And it could vary, it could be a lot more, it could be a lot less, but averagely you see that. Just think about what that means, okay? A centimeter. How big is a centimeter? I used to tell my students it was about the size of your eraser, but I think more accurately you could say the size of a Cheerio, the diameter of a Cheerio. A little Cheerio, we've all had the tasty bowl of Cheerios, and if you can imagine that diameter from one side of the O to the other side of the O, that is about a centimeter. Now imagine that being a cube instead of a little ring. Imagine it being a cube. That little Cheerio's like, you know, a cubic centimeter. So imagine that size. Now imagine 1 atom in that space. Now to get an idea of how extremely vacuum that is, how extremely nothingness that is, first you have to understand how big an atom is, and second you have to understand to compare it to how many oxygen molecules there are in the same space, a cubic centimeter, and how many water molecules there are in a cubic centimeter. To understand the size of an atom, let's start with a meter. Okay, to understand the metric system really helps here, because if you understand what a meter is, then you can know what a centimeter is, and a millimeter, and a micrometer, and a nanometer. And when we talk nanometer, we're getting close. So a meter is about a doorway. When you go through a doorway, it's about 3 feet and then some, 39.37 inches is technically a meter, but about a doorway. Think of a doorway. Now a cubic meter would be like a big fish tank, and I'll show an insert of a picture of a guy who made a cubic meter, and so that's about a meter. Now a centimeter, centa meaning 100, that's a meter divided by 100. So if you cut that doorway distance from here to here, left to right, not up and down, it's left to right. That doorway, about 3 feet or so, you cut that up into 100, that's a centimeter. And of course, that's where you have it about the size of a Cheerio. Now then you have a micron, or a micrometer. That's a doorway, a meter, divided by a million. Okay, now we're talking 6 zeros. It's a lot of cuts to cut up a doorway from left to right. Now we're talking about roughly the size of a spider web silk. If you took one of my human hairs, these nice little gray hairs, that's about almost 100 micrometers or microns. And that's pretty thick compared to a spider web strand. Now a spider web strand will be, we'll just estimate that down to 1 micrometer. You can easily see a human hair, and there's obviously differences in human hair thickness, but we could say it's about 100 microns. And a spider web silk is about 1 micron. That's like cutting your hair, not like this. If I'm holding the hair strand from up and down, you're not cutting it like this, but cutting it this way 100 times. And then you have a spider web silk, and that you can really only see a spider web silk if there's light shining on it. Now that's how small a spider web is. Now we're talking 1 to 3 microns for a spider web. Now imagine that little line going from here to here. Now cut that 1,000 times. And now we're at the nanometer scale. A spider web silk cut 1,000 times, and that's getting close to the size of an atom. If you cut that again 10 times, now we're talking around the size of an atom. Now imagine that little diameter of an atom. You know, 1,000 cuts of a spider web, maybe 10,000 cuts of a spider web, and now we're talking the size of an atom. And an atom, 1 atom per cubic centimeter. 1 atom in the middle of a Cheerio. That's the kind of density we're talking in outer space. There's a vacuum out there. There's not a lot out there. Now, when we compare that incredibly non-dense interstellar medium outer space atmosphere to the atmosphere in the Earth, if you have 1 hydrogen atom per cubic centimeter, and then when you compare it to here, you have 5.3 times 10 to the 18th power oxygen molecules in a cubic centimeter. I'm going to repeat that for you. 5.3 times 10 to the 18th power oxygen molecules in a cubic centimeter. That's like the number 5 with about 18 zeros. We're talking quintillion. That's a lot of oxygen molecules just right in front of my face in a cubic centimeter, the size of a Cheerio. Compare that to 1 hydrogen atom in outer space. And again, when you compare that even to the density of water, water has 3.3 times 10 to the 22 molecules per cubic centimeter. So it's a much greater number, 1,000 or 10,000 times greater in that measurement than the density of the air, of the oxygen. So I'm just reiterating the point that all things have their place in that little science experiment in the lava lamp. And if all things have their place in that little lava lamp experiment, and if a submarine works, and we've mastered going to the depths of the ocean with a submarine safely, then could we not master an airship? Can we not reimagine the airship without having the extremely dangerous, compressed, highly dense amount of hydrogen within? Because we're talking 1 hydrogen atom per cubic centimeter. If you can get a bottle of outer space and you can capsule it, if you could stick it in a tank and bring it back here, could you not create the movie Up? I say you can. It's got to be possible because everything has its layer. And all of a sudden flying, as we know it, doesn't become such a chore. Now here's where the science buffs will say, well, we tried that with Hindenburg and the Hindenburg blew up and it was a disaster. Well, the density of hydrogen molecules compressed into that compartment of the Hindenburg is not the same density of the hydrogen molecules or whatever have you in outer space. If we could send Elon Musk up there or whoever's willing to go up there, even if it has to be NASA, then we could have them literally encapsulate space, bring it down, and use it to help us fly. Because the way I envision the future, guys, we need to get up in the sky. Not just with drones, not just with helicopters and airplanes, and more especially drones, but with airships. State-of-the-art airships that can carry huge, heavy projects that can, airships that can build skyscrapers on the top of mountains, airships that can build communities on the top of mountains, because roads will be a thing of the past. Now, even the Hindenburg, in all of its glory and tragedy, you know, it weighed, I don't know, 200 tons. Think about that. You got 200 tons up into the atmosphere, roughly 200 tons, and it carried 21,000 pounds. So that takes a lot of, if you want to carry that much weight with a helicopter, that takes a lot of fuel to gather that much energy to lift that much weight. But the future is not necessarily in fossil fuels. And you know why? Because when you do the research, when you do the studying, you'll see that fossil fuels will run out. And probably within my lifetime. And I'm not exactly real young and I'm not exactly real old. So we have to start thinking of other ways to ensure the future and to ensure humanity's survival. And that means that all of us, not just the scientists, all of us have to be thinking of ways to conserve energy, to save water, especially in the future, and to save energy, to save the fuels that we have, and to make projects that create energy, sustainable energy. Anyway, I'm big on this kind of stuff. Hopefully you liked my little idea, my little thought experiment. I hope we can create the future by thinking outside the box